Okay, we'll begin today's session. So today we'll be talking about transformers. Let me share my screen. Okay, yeah. So right, to begin with, last week we had a session on attention and RNNs and LSTMs. So we got to see how traditional models were created, traditional neural networks dealt with text, in a sequential form. So both RNNs and LSTMs are well equipped to deal with text and sequential data, any sequential data like text, time series or any other thing. So in today's but when we went into RNNs, we looked at some of the problems of RNNs, right? And to solve those problems a few years back, attention and transformers, these attention is a method and transformer is a model. So these methodologies came into existence a few years back, and since then deep learning hasn't looked back. So there has been a lot of advancement in the entire field, and I would say that the entire field has been transformed after these two things came into existence. So we'll first, in today's class, we'll first look at it from the point of view of text, and then maybe it's best that we look at it in the form of text because it's most intuitive in that way. But know this, that transformers and attention has after coming into text, they have been very popularly used in images as well, audio obviously. Yeah, so let's begin this session. So what are some of the famous RNN tasks? One is neural machine translation, one is image captioning. We all know about these two tasks from some of the previous classes. So again, neural machine translation is what? So suppose you have a sentence in English: India got something, maybe independence. Yeah, India got its independence from the British. That's the input sentence, and you want to translate it into some other language like maybe German, French, and even maybe some Indian languages like Hindi, Bengali and so on. So Bharat ko British se azadi mili, something like that would be the decoded sentence, right? So this is a task that has been out there for many years now, and previously people used to solve this using RNNs, right? And how it would go about is something like this. So whatever is the source sentence, that would be passed on to the encoder. Hi Subrat, is there a problem?
Yeah, hi. Actually, I thought no one joined my session. I thought, is there a session going on like today? Or...
It's going on. Maybe, yeah, you can take your separate session because
Yes, yes.
it will
Yeah,
be counted
I'll
for
do
both
that.
of
I
us. Yeah,
just thought I just thought
sure.
that
Yeah, even for me it's like that.
yeah.
So yeah, but we
Is
have
it
to
a
take the
holiday or
session.
something? I'm not sure.
I don't know. I mean, sometimes it happens. So last year also it happened. So it's okay. I mean, we have to just take the session so
Okay,
that people can follow it later.
okay. Thank
Sure,
you. Yeah,
sure.
I'll do that.
Thanks,
Sure.
Subrat.
Yeah.
Yeah, okay. Okay, so following on, yeah. So we were talking about machine translation, right? So previously what used to happen is the source sentence would be sent to an encoder, right? And the encoder, so the encoder would be an RNN, right? So the RNN, what would it do? It would basically take into consideration all these words individually, right? So it would be passed to the entire RNN, And like I told you last class that the last maybe the last hidden state of an RNN, the last hidden, by last hidden state I mean the hidden state corresponding to the last word, that is very often used as a maybe some sort of a summary, right, or that is generally attached to another vector which might contain some sort of a summary of the source, right. So this is the encoder. So you encode everything in the RNN, your source sentence, and you pass on the last hidden state to something that we call a context vector, right. And this context vector then serves as input to the decoder, which is again another RNN, right, which is trying to predict the correct Hindi words, right, if we are translating from English to Hindi, correct. So from the encoder sentence we are moving on to the context vector, and then we are going to the decoder, and this context vector is supposed to consist of the summary of the entire encoder, right. So what is the problem with this? Problem is that whatever we told last time, that RNNs have a huge problem of vanishing gradients, right. So what happens is, when you are at this point, right, when you are at the word British, right, so RNNs, because there is this vanishing gradient problem, it already forgets the initial words of the sentence by the time it is here, right. So since this part only is connected to the context vector, so the context vector is only connected to the last hidden state, right. That means what? That even this context vector, which is supposed to contain all the information here, doesn't know too much about the initial words, right. And when you pass this on to the decoder, right, it doesn't contain too many of the initial words. That's the biggest problem of this method, right. And then you are basically passing an incomplete thing to the decoder, which again has to translate the sentence, and you can understand that this leads to some sort of a faulty translation, right. So that is the problem with the RNN based encoder decoder architectures. Similarly, in image captioning, what is image captioning as a task? So it's a very interesting thing. I don't remember if I talked about it before or not. So previously all the different tasks or architectures that we saw, that would only contain either all images, all texts, all audio, or so on and so forth. So however, like as and when we started doing very well in deep learning, people tried to think that okay, we as humans, we perceive the world in a multimodal way, right. So we interact with the world in a multimodal way. We talk, we write, we see, and so many things. So every action that we do in our lives is dependent on all these different modalities that we can perceive. So image captioning is a very simple task for humans, but very difficult task for the machine to do, wherein the model is given an image and the model has to describe the image in English words or in basically words, right. So this is why it's called image captioning. So you generate the captions of a image, correct. So now you pass this image onto an encoder, okay. So this encoder comprises of a CNN and an FC network, and this encoder's output is then sent to, again this is summarized as a context vector, which is again sent to a decoder sort of, and this decoder's work is to generate the output sentence. So this decoder is kind of like the so this decoder is made up of an RNN, right. But again you can see one thing, that this context vector, right, so it may not contain all the information of the image together. So because CNNs are basically, they do not have, they are meant for spatial okay. So yeah, we were here. So just to give a brief summary of what we have been talking about. So we have been we talked about neural machine translation, where we said that due to the vanishing gradient problems of the RNNs, the context vector, so this is the source sentence and this is the translated sentence. So you are basically you are translating from English to Hindi in this particular task, and the pipeline is like this, that you encode the source sentence first and use its last hidden state to create a context vector, and that context vector is passed on to a decoder, where the decoder's job is to create the translated sentence. But because RNNs have the vanishing gradient problem, the context vector does not contain full information or very good quality information of these earlier time steps. Hence, RNNs, while they used to be the only choice for solving this neural machine translation problem, so this is one of the problems of RNNs. And similarly, this happens for image captioning as well, where image captioning is a task which involves looking at an image and converting it into a sentence, into a caption, hence the title image captioning, right. So here you encode the image, generate a context vector and put it into the decoder. However, the context vector is only present in the initial time step, which is it's the opposite of what we saw in neural machine translation. So it's only given as input to the initial time step, and hence towards the end there is a chance that the RNN might forget what was going on here. So this is why. So these are some of the problems in the practical scenario where we generally used to use RNNs maybe 5-6 years before, and this is why this vanishing gradient problem and the problem of so this vanishing gradient problem leads the model to forget some of the initial parts of the sentence while when the current position is at the end. Hence, people came up with different other mechanisms to basically do away with the problems of RNNs, right. Similarly, another example can be something like this, that again you are maybe translating an English piece of text to German, right. So what are some of the problems? So very often, sometimes when we translate between two sentences, right, translate one sentence to another, the positions of the words in the source sentence, they generally tally with the positions of the words in the destination sentence, right. But in some languages it may happen that the source sentence has these two words which correspond to the last two words in the destination sentence, right. And then when you basically process these two through an RNN, this part the RNN doesn't cannot remember basically, right. But it has to go to the last of the destination sentence, which causes a lot of problems, right. So long term dependencies, as written here, is not the best thing that an RNN can do. Hence I mean, we have to deal with these problems, and this is why attention has become so important, right. So attention is doing what? Attention is saying that okay, here I am looking at I am always in this particular RNN, if you can see, if I am here, I am always looking at only my previous word, and this word is only looking at the corresponding previous word, and so on, right. So there is a like single sort of dependency. So one word at a time is only dependent on the previous word. It cannot see the other words directly. It cannot see the words after. It cannot see the words before. Only the one that is there just right before the current word, right. So so attention says that no, I'll look at all my words around me, okay, and I'll take all the information that is there around me, I'll gather them and I'll combine them in order to get a much better representation, right. So this is what is meant by the term context modeling. So when it comes to attention, transformers and these sort of sophisticated models, this context modeling term, it basically becomes very important, where what we are saying is that we will no longer depend on the previous word, we will always look at the entire context, and based on my neighborhood I learn a representation of my own. So that is how we are going to go. So in this particular slide, so this has been taught by sir, but this is a revision, that suppose this is again another machine translation example, where the x's are the like the source sentence, the y's are the target sentence, right. So what we used to do again in the previous years, that when we used to use RNN, so we would have hidden states like this, right, which would be connected one after the other, and this one, the last one, this would contain more or less the summary of the entire entire sentence, source sentence, which would be sent across to the target sentence, and then the target sentence would again be independently modeled by another RNN, right. So here in case of so you can see one thing, that the dependency of the target sentence on the source sentence is only through this branch, right. It's only through this branch that I am telling the model that yes, you should, this is how you should, this is the source sentence, you should convert it into the target sentence, right. And because of the vanishing gradient problem of RNNs, this particular hidden state itself is not a very good representation of the source sentence, because it forgets the initial parts of the sentence, right. So now what people said, basically what people came up with is that we'll have the encoder and the decoder, that's not a problem, but we'll enhance the decoder's representation so that it contains more information from the encoder, because ultimately our goal is to convert this source sentence to the target sentence, right. So what it does is, at a given time step, say suppose time step t, so we are here, basically our main task, our source sentence is already given, we are generating the target sentence one word after another, and suppose we are at the tth time step, right. So what we'll do is, we'll so in a normal RNN we would have just taken this st minus 1, this is the hidden state of the decoder, right. We would have just taken this one, right. So now instead of doing that, what we will do is, we will perform an attention on the entire source sentence as well, right. So basically what we will try to do is, we will try to get we will try to see this word, right. We will try to see what has been encoded, okay, yeah. So we will try to see what has already been encoded in the previous time step, which is st minus 1, and now we will also right, and now we'll first, just to summarize, so we are performing a machine translation task and we are trying to understand the role of attention here. So what we are doing here is that we are trying to generate the translated sentence at the tth time step, right. So what we will do is, we will see that we will look at the t minus 1th time steps hidden state, and we will try to see what are the important words in the source state based on this st minus 1, right. So then what we will do is, based on the importance, so we will calculate the importance of each word in the source sentence given this st minus 1 in some way, does not matter how. So we will calculate the importance of each of these words. So and then we will convert these importances into some sort of weights, okay. So this, then what we will do is, we will do some sort of a weighted sum of all of these hidden states, where the weights will be based on the importance, like I told, right. So if suppose H2 is very important in for this st minus 1, then the weight for H2 will be very high. If this H capital T is very small, very less important for this particular st minus 1, then the weight here will be very low, right. So what we will do then is, we will calculate a CT, which is this CT vector consists of a very summarized information of the source sentence with respect to the previous time step st minus 1, right. And this we will use on like this summary that we calculated, this will include here in the tth time step to calculate the yth or to predict the yth word, right. So, now going into a little bit of detail of how this is happening. So, like I said, I want to calculate a CT which is like a weighted combination of all my hidden states, right. So, that is given by this, right. So, this T is given by the tth time step where I am currently standing at, right, and this alpha Tj 8j. So, this we are adding. So, this alpha Tj becomes my weights for the tth time step, right, and j stands for the all the source words basically from j equal to 1 to capital T, right. So, we are calculating a weighted sum of all these, fine. And now, how are we calculating the these weights? Basically, we'll try to ensure that these weights all sum to 1, right. So, they are fractions, all of them are fractions, and how we are calculating them is we are trying to see how relevant each of these hidden states are with respect to this st minus 1. So, we have a scoring function which basically calculates some sort of a similarity between st minus 1 and the 8j, right, the individual 8j's, right. We will take that, and so we could have just continued with that similarity function, but we want to do some sort of weighted sum, hence we want the weights to basically be fractions and finally sum to 1. Hence, on top of these scoring functions we add a softmax, right. So, we all know now that softmax basically converts your vector input vector to a probability distribution, and that is exactly what we want, right. So, we want the weights to be like they should sum to 1, they should be probabilities, right. So, we take this code. So, this part basically means that I will try to find which of this given this st minus 1, which of these hi's or 8j's are most similar to st minus 1. They will have higher weights and the others will have lower weights, and based on the weights now I will calculate the context vector Ct, right, and this Ct I will give as input to this st, so that it has now all the information of all these input words. So, now you see that we do not have to just depend on the last hidden states outputs for this sort of a for basically conducting this machine translation. So, that is what is this is an example of attention in the temporal space. So, we know that text is temporal in nature. So, now we will move on to basically the spatial data, right. So, spatial data, so coming to spatial data, the obvious example is an image, right, and suppose we do this sort of a thing. So, we pass the image to a CNN followed by a FC network, right, and this FC network gives us some suppose certain vector S0, but this S0 vector, we all know that CNNs maintain the local spatial relationships, but the moment you use a FC network on top of a CNN, you are losing all those spatial information, right. So, S0 contains no spatial information, it is just like an aggregate vector of the entire image, right. But now suppose it has been shown that if you take an image and if you basically do this sort of context modeling that we did in the previous slide, right. So, if one part of the image is aware of what is going on in the other parts of the image, the representations learnt are much more robust and much more richer in nature, right. So, then how can we apply this sort of attention that we saw here, right, this sort of context modeling that we saw. So, the idea is very simple, that instead of taking the output of the FC network, you take output from the CNN itself, right. So, say suppose the output of the CNN is some m cross n cross c tensor, right, where c is the channel size, right, and this we have seen in the even in the case of object detection also, that these can be projected right back onto the image, right, each of these. So, there is a receptive field and we can project these to the original image, right. So, now what we will do is, in order to perform attention, so we take this m cross n cross c, right, and we take each of the channel vectors, right. So, what we'll do is we'll so this particular yellow one, so this is a vector across the channel, right. So this has a dimension of 1 cross 1 cross C. 1 cross 1 means here there is a 1 cross 1 like cross section, and this is of dimension C, right. So C dimensional vectors basically. So now basically what you have done in reality is that you have divided this m cross n cross C into m cross n C dimensional vectors, right. So you are doing this every time, and now these vectors are like your sequential data, which we similar to what we are seeing here, right. So these become your sequential data like this, okay, and now you can apply attention in a similar way that we showed here, right, and then we get the attention based context vector for the individual locations, right. So this is how we deal with spatial data. So initially attention and transformers, they were created by keeping in mind temporal and sequential data. But then nowadays if you go ahead and look at the current research in image process in computer vision, you will see that VITs or vision transformers have become a very important part of image based research. And so basically transformers are nothing but they are some architectures that are just built on top of this concept of attention. So this has become one of the central architectures in images as well. Now the question that comes to us is, so what is the story behind attention is nothing but you have some vector like this ST1 and you have a sequence like this. You are trying to find the similarity of this vector with the individual elements of the sequence, and then you are trying to calculate some weight with respect to each of these, and then you are calculating a weighted sum and combining the sum with the original vector in some way. That is the story of attention. Now question is, what is meant by this similarity? How do you compute this similarity score at all, right? So that is given by this table. So there are a lot of attention methods, mechanisms that people have used, and there are even more perhaps in this list that have not been shown, right? So whenever we think of comparing two vectors, the most common computation or the most common metric is the cosine similarity, right? So the cosine of the angle between two vectors. So this then ST and HI, the similarity between these two is given by the cosine angle between these two vectors. So cosine is nothing but ST transpose HI divided by norm of ST into norm of HI. That is how we know it, right? It's the cosine of the angle, right? So this is called content based attention. Another formulation that is very popular is dot product attention, which is just direct ST transpose HI. Very similar to this one, just that it does not have the normalization in the denominator. So this is simply ST transpose HI, right? Scale dot product attention is actually what we use in today's world, but yeah, it is basically ST transpose HI, which is scaled by some scalar in the denominator, right? There are other attention mechanisms as well. So some of them, they instead of like using these matrix which are unlearnable, basically they are fixed matrix, they have fixed formula, mathematical formula. So using one way is that you use these and compute the similarity scores. The other is that you learn the similarity between two vectors, right, in this way, right. So this is called additive attention. So this, the formula is given by this, where this sign means concatenation. So you concatenate ST with HI, and then you have this and this, these two are learnable. This is a matrix, this is a vector. So these two are learnable, right. So basically you are trying to learn the similarity between ST and HI through these learnable parameters. So this is another form of attention that is very popularly used. So you can see that very often, so even in location based attention, general attention, these formulations have been used, right. So here also this formulation is very similar to the previous to the next one. So there is a vector transpose, I mean ST transpose into HI, but there is a WA in between where the WA part is learnable, right. So these are some of the very popular alignment score functions where this and additive attention, these three are the more popular ones. Okay. So now we started our class with two of these things, one is machine translation, one is image captioning. So we looked at how to do machine translation, and now we'll take a quick look at what happens with image captioning. So image captioning, like I again said, that it's a multimodal task. Multimodal means what? It involves two two kinds of inputs together, right. So or two kinds of yeah, maybe we can call it inputs. So the task is something like this, that you have been given this image and you have to basically write a text. The model has to output a text description of that image, right. So by looking at this image, one description can just be as plain as straw hat. There can be other descriptions as well, right. So how did the traditional models used to train this sort of a complicated task? Well, it's very simple. So your input is this, right, and this is what you should predict. So what they would do is, they took this image and they sent it off across to a CNN model, right. And in the CNN model, so this is like maybe suppose a typical ResNet model or something, ImageNet pre-trained maybe. And so because of the ImageNet pre-training, you would have you can see here it's cut off, there is a FC of 1000 neurons, right. This refers to the 1000 classes in ImageNet. Oops. Yeah, this refers to this refers to the 1000 classes in the CNN. So because we do not have any class or something like that, we cut these off and instead take the predictions from here, from this 4096 dimension FC, right. And now what we will do is, so like again I said, this is a traditional image captioning system. So what you do is, you have a piece of image which you process through a CNN, you have a piece of text which you process through an RNN. That's the simple guess, right. So now what you do here, normally what we would have done if this image was not here is, we would have trained an RNN like this, where there would be a start token, then straw, then hat. This is how the training would go on, and there would be cross entropy losses on top of this, right. But here because there is an image involved, we take this vector that is generated at the at the output of the CNN or CNN plus FC, and then we pass that on to the initial hidden state, right. So this becomes, so this was the original formulation when only text was involved, and this becomes a formulation when your image is involved, right. So we have x0 times wxh, wxh is somewhere here in this arrow, right, and then we have the image v, right, which is the vector v is given here, this is the vector v, right, into some weight matrix wih, and that is, these two are added to get your initial hidden state H0, right. So this is all about the image captioning task, which we used to do. This sort of a model was very popular in the pre-attention days. But now when you have attentions, what you do is, like we said in this particular when images are involved and you want to do attention with them, you do not go into the FC network anymore. You take the CNN features themselves, so that you will have a tensor like this of some dimension m cross n cross c. So this is what you would do here. So this is your input image, you pass it through the CNN, cut off the FCs completely, take the CNN outputs, right, and then what you would do is, this is your RNN, right. So now what you would do is, you would let the RNN itself learn the distribution of the basically these different, so we have so many vectors here, right. This is what we had seen. So in order to, so this is a simplified version of that. So what we are trying to do here is, we want to to each hidden state we are going to give this as an input. That is what attention is about, right? So we do not have to give the image part as an input right in the beginning of the sentence. We can give it as input to every part of the sentence, right? So what we do here is, now we have all these different vectors, right, in like depicting the different like different vectors here in this channel wise vectors here. So we have all these different vectors. Now attention involves what? Attention involves having some weighted sum, right? So weighted sum with respect to the query vector, right? So what we do here is, the weights that are required to combine these weights are learnt directly in the network, right? So this H0 will predict a A1. So H0 is basically the initial state, initial hidden state, right? So no input is connected to it. So now it predicts an A1. What is A1's task? A1's task is basically, A1 is a set of weights, right? So when you have this input, so it will be useful in this stage, right? So A1 is nothing but a probability distribution, where each probability value gives you how much weight you want to give individually these vectors, right? So now based on the weights that are given, that are learned here, you generate one vector out of these, right? That is given by Z1. So in the first time step, alongside the first word, which is Y1, you give this Z1, which is like a summary of the image based on your previous hidden state, right? Then you generate this H1, and H1's job is now to generate two things, right? So the first thing is the first word maybe, right? The distribution over the vocabulary like we have learned, and obviously the distribution or the weights of the image features based on the similarity, right? So this you go on continuing. So every time, at every time step, you basically, these AIs, they are like predicting what is the probability distribution and what are the weights which I need to combine, with which I need to combine these vectors here in this matrix, so that I can send it as an input to the next time step, okay? And then that, so this is like a summary of the image here that you are sending here, and this is the current time step, and this you are sending to the hidden state at this time step, and then you are generating again two different things. So this is how image captioning with attention is used, right? So this model has been has been shown to be far better than this one. Why? The reason is that here you are using first of all this FC layers, where there is no spatial information, right? It is just an aggregate, right? If there is no spatial information, then basically you can understand the difficulty, right? So if you had just sent an aggregate, there are so many things going on in this image, right? There is a man, there is a hat, there is a background, etc. So if you had only used this sort of a summarized vector, it would have been very difficult to like incorporate all this information into this single vector, and how like different maybe the hat is on top of the man and so on, all these spatial relationships would be lost. And hence the next, what attention people did is, instead of taking the FC layers here, they would use the CNN outputs or activations from here, and then they would combine them with the RNN inputs through attention, right? Okay. So now coming to transformers. So transformers are nothing but they are I mean you can say that they are some sort of a deep learning architecture, which basically whose central point is nothing but attention, right? So there are multiple parts in a transformer, like self attention, multi-head attention, positional encoding, and finally the encoder decoder architecture, right? So we will go through all of these individually, right? So all of these subparts basically like kind of they are what transformers are made of. So a typical transformer would look something like this. So there's there is an input sentence which is probably in some other European language, and you pass it through layers of encoders, and then that, so there is a output sentence also which is what the model should predict. So you should pass the encoder's information to every decoder layer and then have this as output, right. So previously what used to happen is, like in the like again going back to the RNNs, only the last layer's information would be passed, and that too only in the beginning of the decoder. Here that situation has changed, so we pass information from every layer to every layer, right. So this is what is known as, so this is what is the crux of transformers, right. So instead of going through this complicated architecture here, it's better to break it into step by step, in a step by step fashion, so that the revision you are well revised of what is going on. So first thing is positional encoding, right. So positional encoding will it's a little bit heuristic, but the concept actually makes sense, right. So again if we go back here, our main point was that in the RNNs we are only looking at the previous word. So here we'll try to have a look at all the words in the sentence, right, in order to get a good picture of the context, right. But in this entire formulation, you are seeing that there is a weighted combination of these vectors and all. So you are combining the information of all these vectors, but in some sense, in order to combine these, you are forgetting which part of the, have you included anything about the position of each of these? No, right. So you are blindly just computing the weights, multiplying them with the h values, and then you are taking a weighted sum, where you are not telling the model at all that which word came first, which word came second, right. So in RNNs that problem was not there, because in the RNNs there was only a unidirectional flow, right, not a multidirectional flow like this. So RNNs did not require this, but in case of transformers, since you are using kind of everything, you do require something which will tell the model that okay, what is, I mean this hj, which position in the sentence is hj located, right. So in order to do that, yeah, this positional encodings came into existence. So it's very difficult to if somebody goes to the paper of attention is all you need, all the explanations are given there as to why the positional embeddings were like this, but this is what the authors used, and hence this is what is taught, right. So what you have to do here is, if you are at a position which is so if you are at the maybe like even positions in the sentence, then you use this sinusoidal function. If you are at an odd position, then you use this cosine function, right. So this pos is basically the current position, and this 2i, this I is basically the position of the like we were saying, this I basically refers to which position are you here, where you are the one that you are using to sum up, right. So this is how, this is the formula. We will not go too deep into this, but this is what the authors came up with, and this is what is used nowadays. Some architectures are not using positional encodings anymore, but yeah, typically we still use it. So using this sinusoid, these two sinusoidal functions, right. So it all depends on the position of I. So if it's an odd position, then you use this one. If it's an even position, then you use this one. So what you do is this, you already have a initial word embedding here, right. So you already have these initial word embeddings here. Now for each embedding, you also calculate the positional encoding, right, and then you concatenate or sum them. So there are again multiple variants. So generally people concatenate. So once the positional encodings are available, you concatenate those encodings with these input embeddings in order to make the vectors of or the model aware of what position the individual words are lying in the sentence, right? So it helps in maintaining the order of the words in the sequence. Right. So now coming to self attention, right? This was the point that we had started with. So self attention, previously in the neural machine translation or in image captioning, what we showed is attention is between two different things, right? So in neural machine translation at a certain position t, we were trying to find the similarity of st minus 1 with the all the words in the input sentence. But note here that when we were doing this sort of a neural machine translation based attention, we were actually in the decoding space, right? And this is, so we were calculating the similarity between some vector in the decoding space and some other vectors in a totally different encoding space, right? So this is similarly in the image captioning also, the picture that we saw here. So it's like attention between the individual words in the sentence, right, in the target sentence, and the different parts of the image that we wanted to perform attention on, right. So this is what we saw as attention. However, self attention, this entire slide, so self attention basically refers to the fact that you want to apply attention to yourself. Okay. So basically it's like given a sentence or given a word, I want to perform attention on myself, right, given a sentence, given a word in a sentence, right, which would mean what, that as a word, right. So yeah, it's okay. So as a word, what I would like to do is in a given sentence, I am just a word in the sentence. So what I would try to do is, I would try to, so normally I could have used only suppose a word to vec embedding or some other embeddings that are very popular in natural language processing to represent that word in the sentence. But now we are saying what, that is not enough, right. We want that particular word to not only know what that word means, but also be aware of the other words in the sentence, right. So that is where self attention comes in, that I'll incorporate the context that is around me as a word into my own representation, and that will enrich my own representation to a great extent, right. So in other words, what happens is, so generally when we do attention on image captioning or the other tasks, right, like neural machine translation and so on. So one modality becomes, or one space, we get the query from one space and key and value from the other space, right. Here they all come from the same source X, that is what is self attention. So X is your input sentence, suppose there are two words in X, suppose. So this is row wise maybe, right. So there are two words in sentence X, like here it's given thinking machines. So this is just one sentence where there are two words, thinking and machines, right. So now you convert this X into query using some weight matrix WQ. Similarly, you convert the same thing into key using some projection matrix WK, and again into value using WV. So here you can see the X's are always the same, the weight matrices vary, and you get Q, query and value separately, but they are coming from the same source, right. And now what you do is you simply use the attention formula. So you have the K matrix. So here now we are converting everything into the matrix space, because that is the easiest thing to do when you are coding up, right. So you have the query and then you have the key, right. So always you are trying to, the story of attention is that given the query and the key, you are always trying to find the similarity between these two, and that gives you the weights, and you are now simply doing a weighted sum of the values using the similarity scores, right. So that gives you a much more enriched information, right. So here you take the queries, and so in order to convert the story that I told, So this is how you do it in terms of in matrix notation. So qk transpose by some root dk, right. Root dk is basically the dimension of the keys, right. So this you pass through a softmax. So softmax is basically giving you the probability distribution, and that you multiply with this v. So that will basically add so perform a weighted sum of the these value matrix, right, and the resultant output is going to be z, right. So this is a much better like context rich representation of your original x vector, right. So here like x is, so there are two representations, two vectors in x, this first row and second row, and z has these two similar corresponding representations in the first and second row, right. So each of these are like the like much more context heavy, context rich representation of the individual words in the X matrix. As an example, something like this can be thought of. So like I said, there are two words, suppose thinking and machines, right. The embeddings, the original embeddings are given in x1 and x2, right. So from x1 and x2 I can generate the query key and value matrices. Here we, for simplicity, let us we have broken the matrix into vectors for corresponding to the individual words. So we have a q1, k1, v1 corresponding to x1 and q2, k2, v2 corresponding to x2, right. And then what we do is we are simply doing a dot product here, as you can see. So that can be given by, so dot product means what? This row multiplied by this column, right. So basically we are performing q1 dot product k1, suppose this is 112, right. Again we are performing q2 again we are performing this q1 dot product k2, right. So that is basically giving us something like this, some value like this, and now we will scale it, right. So this root over dk, so dk or the key vectors value is generally, dimension is generally 64. So root over of that is 8. So we divide by 8. So this is some scaling factor which has been shown to give very good results. So we divide both the quantities by we can divide both these quantities by this particular quantity, and then by doing a softmax we see these two values, so 0.88 and 0.12. So this is basically, you can understand that this so here what we are trying to do is, so this is the query, here we have computed it against q1, right, both of them are based on q1's dot product with k1 and k2. So that means that here we are trying to calculate like for this x1 vector, how important is the x1 vector itself for like x1 vector itself, and how important is x2 for understanding the meaning of x1, right. So here we see that x1 is similar to itself with a 0.88 score, and x2 has a similarity weight of 0.12 with x1, right. So now what we will do is, we have the value vectors already, right. So we will do a weighted sum, this 0.88 multiplied by v1 and 0.12 which is much lower multiplied by v2, hence you can see that the color has become very light, and we will do a weighted sum, and that will give us basically z1, right. So this is how z1 is calculated. So this z1 basically consists of a combination of information from both thinking and machines, where I am trying to see, like, given the original embedding of thinking, how important or what context information can I gather from the other words as well, right, and the combination leads to this z1. This z1 we are going to concatenate with x1 in order to get a much more context rich information. So that is what is known as self attention, right. So here again the story is something like this, that based here all my x's are going to remain same, which is not true for machine translation and other tasks. So there the query comes from one source, and key and value always comes from other sources. Here we are saying that for self attention, everything has the same source, right. So, given a particular word, I am trying to always see how important is that word or how important are the different context words with respect to this input word. So, that is what the example given in this slide depicts. And finally, we have multi-head attention. So, multi-head attention is doing what? So, we have these two embeddings again in X, and now instead of, so here we showed like how we can convert like an input to query key and value. So, but this vector or these matrices that convert certain input to query key and value, they may only capture one relationship between the different words in a sentence. But English, the language, can be so complex. Anything came up? Okay, fine, sorry. Yeah. So, the language can be so languages can be so complex, even images, that between two different things there can be multiple relationships. So, in order to model these multiple relationships, multi-head attention came into existence, which basically in very simple words it said that instead of having one such triplet of QKV, we will have multiple triplets, right. So, we will have something like this, we will have a W0Q, W0K, W0V, which will give us Q0, K0, V0. Similarly, we will have Q1, K1, V1, and in the paper they used 8 such different versions. So, Q7, K7, V7 starting from 0, right. So, we have 8, right. So, we basically, this means we have different query key and value matrices, and how many different? Basically 8 different query key and value matrices, which gives us all these Z0, Z1 and Z7. So, there are 8 such resulting vectors that we are getting for each vector in X, right, and we will pass them on, we will pass them through a weight matrix WO, right, in order to, and basically like it is given here. So, we will concatenate the resulting Z matrices. So, this Z1, Z2 to Z7 we are concatenating, and then we will multiply them together with some weight again a learnable weight matrix W0 to produce final output Z, right. So, this is what is known as multi-head attention, right. So, good. So, after knowing the different parts of attention, so we will now have a quick look at the different. So, these, the parts that we saw, these were basically the building blocks of the transformer architectures. So, now the final thing is the encoder decoder architecture, right. So, transformers may have an encoder, a decoder, and sometimes only encoder. So, it is important to understand what happens inside an encoder and what happens inside a decoder, right. So, this is a typical encoder architecture whose which is zoomed out in this way, right. So, what happens inside the encoder is, we have again suppose two words, thinking and machines, right. We add the positional encoding here. So, this is how we add it, right. So, we have a very nice piece of code after this code walkthrough, which will give us more ideas, which will be shared with you. So, positional encoding we are adding first, right. So, then so this happens here, right. So, this gives us maybe some revised version of x1 and x2, right. Then we perform self attention like we showed, and we are getting two vectors z1 and z2, right. So, now then what happens is, this using some sort of some concept which is similar to residual connections, using some concepts which is similar to residual connections, maybe we are taking these x1 and x2 and we are adding them to the z vectors, right. So, we had x1, x2, we did self attention, we got z1 and z2. Now, this X matrix, which consists of x1 and x2, is combined with the Z matrix, and then something called layer norm is performed on top of these. So, layer norm, you can go back and have a look at what it means basically, right. So this layer, entire layer is called add and normalize, right. So we are adding sort of a skip connection or a residual connection, and then we are normalizing in this layer. So that is given by this layer norm, right. So that is giving us again some revised Z1 and Z2. So all of these are matrices, right. So they can be separated into vectors. That is what is happening here. So from here we got a Z1 and Z2, and we now have a feed forward neural network on top of each of these, right. And then so that gives us some other, maybe some other vectors, maybe some y1 and y2, you can say output of this, and then we again have this sort of a add and normalize layer, right. So this layer is again repeated on top of this, right, where your residual connection basically flows from these pink sets, this sets, right, and it is added to the output of the feed forward neural network and then normalized, and that becomes your output of this entire block, right. So now when we began, we gave a picture like this, that like a transformer encoder can be like this, that there's multiple layers on top of each other, right. So then what you can do is, this is like this entire picture, and so these two are equivalent pictures, right. So these are, this self attention is basically multi head attention, which is given here. So and then you add this add and norm layer, and then feed forward and add and norm, and this you repeat for some 5-6 times, right. Standard count is 6, but yeah, I mean in modern times maybe people vary these and do different lots of stuff, right. So you place these layers one on top of other for 6 times, and the resulting architecture is the encoder, right. Now coming to the decoder. So the decoder basically, if you understand, so it has the decoded input, right, in the training stage, and some help from the encoder as well, right. So going by this like this picture once again, so it needs input from the encoder, and it has its own input to be able to learn, right. So yeah, so in the decoder, correct, so in the decoder what we do is, again we have the architecture is very similar, you can see. So this entire thing is a block which we call decoder block. Similarly this is an encoder block, right. So this decoder block is repeated again 6 times, but what goes on inside this is that first, so previously there was a multi head attention, here we have a masked multi head attention, right. So why masked? Because again when you are, suppose you are trying to translate this sentence to an English sentence, right. So the output is I am a student, but when I am at timestamp A, timestamp 3 maybe, where I am at this location A, I do not know what has happened in the future, right. The student word is futuristic for me, right. Hence I will not apply this attention on this particular word, I will ignore this word when I am at this time step. So attention is what? When I am at time step corresponding to this word A, I will look at all the context that is around me, and I will try to summarize them and add them to my representation. So that is what attention is all about, self attention is all about, right. But when I am doing the self attention in a decoder, this word is not supposed to be there. Hence I will not perform I will not take this or any other word in the right side into consideration when I am looking at the context. That is what is meant by masked self attention or masked multi head attention, right. So this is how first we perform masked multi head attention and do an add and norm layer. So this is similar to this part, right. So this entire first part, this is what we perform. And now because the decoder is dependent on the encoder, now some input is going to come from the encoder as well, right. From the encoder layer, the help is some source of information is going to come. So they become your, so this becomes your query, the parts of the words in the decoder, they become your query, and these the key and value is supplied. So hence there are 2 arrows, the key and value are supplied by the encoder, then you have a add and norm, right, and then you have the feed forward and add and norm, right. So these 2 parts are basically similar, the top and the bottom parts are similar, it's only the middle part that is a little bit different, right. So this is what we started with in the class. So like the key and value coming from the input sentence, and the query part it's coming from the translated sentences previous word. So this is also repeated 6 times, and that makes your complete decoder. So this is finally the architecture, as you can see. So this arrow was missing, the source of this arrow was missing in this slide. So that is completed here. So at a some layer I, some encoder layer I, you take the encoder output and pass this on for multi-head attention with the decoded input, right. And the only thing that you have to remember is that here we have masked multi-head attention. So masking is required. So we will see a good example in the codes also. So yeah, oops, yeah. Okay, so when I shared this code with you, you will see that this code is actually remarkably detailed, right. So it has a lot of information in it, and actually when you look at it, it's going to be so self-explanatory that you will have a good time going through this, right, when you go back to it and look at it on your own time, right. So it first of all, it explains all the individual parts of the transformer very clearly, very thoroughly, right. So how these so this is the encoder architecture that you can see, right. So and this is the on the left, on the right side there is the decoder architecture, right. So it's the again the input sentence is something like hello I love you, and so you encode this, right, and then you go on and you pass this information to the decoder, and the decoder's output is something like this. So looks like French, right. So this is what is meant by self attention, right. So you have 4 words in the input, right. So these 4, so we can call them x1, x2, x3, x4, right. So that makes your matrix, and then your X matrix that we saw previously, and then you have these WQs, WKs and Vs, which give rise to your query key and value, right. And then you perform attention, where you have to remember this a little bit, because this is very standard softmax of KQ transpose by root over dk into V, right. So this is basically in a nutshell the dot product sort of attention that you are performing in the vector notation. So this is just a matrix notation of that, right. So this is a nutshell of the transformer architecture that we begin with, right. And then we'll go on to look at some of the like some of the smaller parts of attention and how that is coded up. So note that this notebook doesn't show how to train transformers. You will find many such notebooks on net. So this basically gives you like very thoroughly written code on the individual sections of attention, right. So if you have missed something in the lecture slides or missed something in the TA sessions as well, this is where you should look at to get a good feel of what is going on in attentions, right. So here they say that so now if you look at modern PyTorch codes, multi-head attention and all these things, transformers are already available as black box modules maybe, but here we are explaining this paper attention is all you need. So attention is all you need is basically the like the father of transformers. So this is what introduced transformers to the world, right. So this entire paper is implemented from scratch in this particular code base, right. So and this is meant for the encoder decoder architecture, okay. So here you can see that a blog also has been referred, right. So you can just go through it, where this person has, so this is a very famous blog where there is an in-depth explanation about the working of the transformers, right. So this is the picture more or less that we saw, that there is an input which is encoded, and then the encoder input is sent to the decoder and you get an output. So this is the example is again machine translation, right. So like it says here that the above image shows a language translation model from French to English, right. And like we talked about. So, there are 6 encoder layers here, 1, 2, 3, 4, 5, 6 and 6 decoder layers, right. And now this is the bad and complicated picture maybe, right. So, this is the full image of the encoder decoder transformer, where encoder and decoder are very similar, just that there is a middle layer here which performs attention between the encoder layer and the decoder layers, and there is must multi-head attention in the decoder. That is the only difference. Now, the question is that, so let's ignore the import statements, you can look at them on your own time. The first thing that we need to do in learning transformers is to create word embeddings, right. So, what we need to do here is, so like we saw in the slides as well, always the beginning is a word embedding. So, we begin with word embeddings and then we move on to things like hidden states if required, or we can directly deal with the word embeddings themselves, right. So, word embeddings are what? So, since models do not understand words themselves, right, they represent everything with respect to numbers, and we have seen that good way to represent any entity in the eyes of a model is to convert them to a vector space and learn the individual embeddings, right, which will give the which will tell the model the semantic meaning of the word, right. So, now what we want to do is we want to learn. So, again transformers as a whole, it is basically some sort of a one application of that is representation learning, right. So, when we are doing attention, we are, or self attention, you can think of it in this way, that self attention basically gives you enriched information of your context, right. So, it is basically some representation learner, both self attention and normal attention. So, what they are saying is that suppose each embedding vector is of 512 dimension, right, and we have a vocabulary size suppose of 100, right. Oops, sorry, yeah, we have a vocabulary size of 100, right. So, this is all, 100 is the number of words that we have in our list. So, we have a embedding matrix of size 100 cross 512, right. This matrix will be learnt on training, and during inference each word will be mapped to the corresponding 512 dimension vector. So, we are trying to learn a 512 dimensional space, right. So, and in that particular space each word is mapped as a vector, right. So, we are trying to learn that during training, and that during inference we will be able to map, right. So, suppose we have a batch size of 32 and a sequence length of 10, right. Sequence length, here we are dealing with sentences, right. So, that sequence length is given by 10 words, right. So, if our batch size is 32, then the output will be 32 cross 10 cross 512, right, because we have a batch size 32, we have 10 words in each sequence, and each sequence has a each word is of dimension 512, right. Here what we will do is, this entire thing is going to be learnt, okay. So, we are in this next part of the code we are initializing the embeddings, but these have to be learnt, right. So, this is how we initialize the embedding. So, we have this self dot embed, which is a nn dot embedding of dimensions vocab size into embed dim, because it is like a dictionary of embeddings, right. So, this is what we are going to learn. So, we have 100 words in the dictionary and we have a 512 dimensional embedding dim. This is what we are going to learn, right. Okay. Next step in the transformers is to apply positional encoding, right. So, positional encoding, we know its formula is given by this part, right. So, yeah, its formula is given by this part, okay. So, here so here like you can see, POS refers to the order in the sentence and I refers to position along embedding vector dimension. So, if the position is odd, then we will use cosine, if the position is even we will use sine, that is it. So, there's, you can see there is a lot of information here which you can go through on your own time. So, this is very handy and very beautifully written. So, the idea here is given by this picture, that if we have a if we have so many input words and this is our embedding vector, right. So the input sequence matrix will have a dimension of sequence length cross the embedding size, right. Now what we are going to do is, so based on the words we will find out the positional encodings as well, right. And so we will also have a similar matrix like this which we are going to add, correct. So this gives us our final input embedding, right. So we will have a so as it is written here, the embedding vector will be of dimension 32 cross 10 cross 512 and the positional encoding vector will also be of size 32 cross 10 cross 512, and we are adding both, right. So the code for this is given by this. So you can see that for every code every piece of code that we have in this code base, there is a very thorough detailed explanation on what is happening, right. So you can see that, yeah, so you can see this, right. So this gives you your sign, the positions and the POS and the I's, right. So from here, if there is any doubt on what POS means, what I means, you will get from here, right. So for the odd positions you are using a cosine, for the even positions you are using a sine, that is it, okay. This is how you calculate the positional encodings. And now what you do is, in the forward function you already have the x, right, and then you do a x equal to x plus the positional encoding, right, and you make requires grad here false because this part is not trainable, right. So this is the positional encoding part, and now you will go to the self attention part, right. So self attention, what is self attention? So we have a sentence like this, that dog is crossing the street because it saw the kitchen. Now the question here, and also where RNNs fail, is what does this it mean, what is it referring to, right. We know that it is referring to dog, right, but RNNs, because they forget everything that is there, so you can see that it is so much distance away from dog, so very naturally it will forget the word dog by the time it reaches it, right. So this is what we are trying to avoid for in the attention process, right. So yeah, so we know in the self attention, always remember that the step that we need to do is to create the three vectors from the input vectors, right. So the query vector, key vector and value vector for each word, right. So each of these vectors in the paper was said to be of dimension 64. That is what we saw in the slides, because the square root of 64 was 8, and that is what we were dividing with, if you remember, right. And so there are a lot of details here, right, which we may not go into, but yeah. So here you can see that we have already given you hints like what happens when you have a batch size of some 32, sequence length 10, embedding dimension 512, right. So here we know that the positional encoding and so we already saw that when we take the embedding and positional encoding and we add those two, the dimensions turn out to be the same, it is 32 cross 10 cross 512, right. Now this we are resizing in this way, right. So it is basically 32 cross 10 cross 8 cross 16, okay. So this 8 is basically referring to the number of heads in the multi-head attention, right. So we are resizing this part 32 cross 10 cross 512 to 32 cross 10 cross 8 cross 16, okay. So 68 is the, here 8 refers to the number of heads in the multi-head attention, right. So now second step is to calculate the score, right, this Q into K transpose, right. So this is the resulting value that we want. So all our query and key and value vectors will be of dimension 64, that you can see here, right. And because we want to generate 8 such values because of multi-head attention, this 8 is coming here, right. So Now, so you can go through these details. So, Q into K transpose is what you need to perform here, right? And step 3 is to divide the output matrix with the square root of dimension of key matrix and then apply softmax over it. Okay, this is the third step. Fourth step is, once we get all of this, we multiply it with the value matrix. Okay, and finally we will pass this through a linear layer, which is the output of the multi-head attention. So, this is the WO matrix that we saw, right? Okay, cool. So, this is what is the code for multi-head attention, right? So, you can see that we are creating the query matrix, similarly the key matrix and the value matrix here, right, and similarly the output, right. So, output has number of heads into the single head dimension, right. Single head dimension is given by this quantity, you can see that, okay, which is 512 by 8 equal to 64, right. Okay. So, given all of this, this is what we are going to do. Okay, so we have the key, query and value, right. So, yeah, so then we are going to find the product of this, right, torch dot matrix multiplication of Q and K transpose, right. And now this part we will look at later. So, we are in the, if we think of the encoder, mask is not there at this point. So, mask we can ignore for now. So, then we do this product is divided by the square root of the dimension, right. So, square root of 64, which is 8, and then we simply do a softmax, and once the softmax is done, we do a matrix multiplication of the softmax course and the V matrix, right. And then you can see from here, from the name itself, that once you find this matrix multiplication, you concatenate this, right, concatenate all of these and finally pass them through this linear layer, okay, which was defined here. So, self dot out is equal to nn dot linear of this thing, number of heads into single head dimension into self dot embedding dimension, right. So, this is your multi-head attention. So, all of these modules we are defining one by one, right. So, the self attention and multi-head attention, we have combined them together in this section, and now we come to the individual encoder and decoder, right. So, we first have the input, which passes through the embedding layer and the positional encoding layer, and then it will be passed through the multi-head attention layer, right. And then next step was what, if we look at this particular diagram. So, we have multi-head attention first, and then we will add the input with the multi-head attention output and do a layer norm, pass it through a feed forward neural network, and then repeat this add and norm layer, and we will repeat this 6 times, right. So, that is what the code here does. So, here you can see that we are calling the multi-head attention class here, the object of this class here, right. We have the 2 layer norm initializations, one layer norm is here and one is here, right. And then we have the feed forward layers as well. It is actually, when you think of it, it is not very complicated if you follow all the codes very thorough. If you follow whatever is given in the formula in the mathematics part, it is actually pretty straightforward, right. So, you have this multi-head attention output here, right. You are then finding the residual output. So, it is attention out plus the value, right. Now, then there is you are applying this layer norm here, okay. So, this layer norm part is applied on the attention residual out, and then a dropout is applied on that, right. And then this norm 1 out, this variable, so we pass it through a feed forward neural network, right. And then we again compute the residual of this, and finally we do again layer norm with the norm 2 here. So, these two are different layer norms, please take care of that. So, that is performed and that becomes the output of the encoder. This is a encoder transformer block, right. And similarly, now transformer encoder is what? It comprises of 6 such transformer blocks basically, right. That is what is given in this for loop, right. Now comes the decoder. So, that is all about the encoder, right. Now coming to the decoder, what is different in decoder is there is a masked multi-head attention and there is multi-head attention coming from the encoder once again. So, step 1, again the output gets passed through the embedding and positional encoding to create embedding vector of dimension 512. Step 2, the embedding output gets passed to a multi-head attention layer, right. This time it is going to be, so the major difference as written here is that we need a mask, okay. So, mask is why again, because I am not supposed to look at, because I am in the decoder, I am not supposed to look at the next future words, right. So, an example is given here that I think I used a similar example, oops sorry, yeah, okay, yeah, the example was this, that for like if the sentence is I am a student, we do not need the word a to look at the word student, right. Hence what we do is we create a mask matrix like this, okay. So, this is for the first word, this is the second, third and so on. What we do here is, in this one I am saying that I will only look at myself and none of the ones in the future. In this one I am saying that I am going to look at myself and the previous one, but none of the ones in the future. Similarly, you go on increasing the ones just to say that I am going to look at myself and all the previous words, but nothing in the future, right. So, this is what is called mask. So, this mask you create and you pass it on so that your attention is not performed on any of the future words, right. And so, now step 3 and step 4, the rest of the steps we know, right. So, that the after the masked attention, the next step would be to have a multi-head attention with respect to the encoder, and finally there is a feed forward neural network that we saw here, right, with an add and norm. So, the add and norm part is common, right, okay. So, this is the decoder block. So, there is a self dot attention, again a multi-head attention block, right. There is a layer norm, there is a dropout and there is a transformer block, right. In the transformer, yeah, right. So, we compute all these things. So, this is just this decoder block, this basically yeah, this describes this part, this part, right, okay. So, then we have this attention, we perform the layer norm with the add and norm step, and then we pass it on to a transformer block, okay, good. So, now this is just one block and this we are going to repeat for multiple blocks, right. So, that is what is given by this transformer decoder function. So, you can see that this is repeated across multiple layers. And now the final code, this code basically comprises of everything in the architecture, right. So, you can see that there is a encoder, there is a decoder, right. The encoder consists of a transformer encoder, decoder consists of a transformer decoder class. So, all of these again you can go back and refer, they are just above, right. And then there are different functions for encoding and decoding, right. Okay. So, now after defining this piece of code, what has been done is that, like I said, this piece of code does not train anything, it is only meant for, yeah. So, it is not training anything, it is only meant for just showing you, giving you a feel of what the code looks like. So you, when you yourself code, you do not have to make things so complicated, because nowadays everything is black box, so there is a lot of code automatically available for you. You do not need to define all of these by yourselves, but this is just to give you a feel, right? So now they have created a, so we have created a source and target sentence, right? So you can see that they are numbers basically. So all, both of these have two words, right? So these numbers are basically token numbers that we got introduced to last week. So we do not give the actual words, but rather we give the token numbers, right? And we pass it on. We initialize a transformer model with its encoder and decoder, right? And when we go below, yeah, so this is what happens in the inference state. So you are not training anything, hence you cannot like expect any proper output in the target. But yeah, I mean this entire, so this is a very detailed piece of code, right? So this will be shared with you latest by tomorrow. So again, like if you have any doubts on what transformers are, what they do, like multi-head attention, what are the different layers doing, how is encoder different, how is decoder different, all these answers. So because, so theory is one thing, but when you look at code, things become much more clearer. So my advice would be to go through this in great depth, read everything that is there here, because I mean we have taken great effort in building this for you, creating this for you, because it consists of so many details. So just go through it and like try to understand wherever you have some maybe cloudy areas in transformers. It's not easy to understand in one go, so there's a lot of thing happening here. So maybe go through these and you'll have a much better understanding, right? So fine, this is all I had for today. So if everything is fine, then let's meet next week then.
Thank you, ma'am.
Yeah. Yeah, this material will be shared, right? So this is very like very detailed code base, right? So you'll find this, I'll share this with you. Okay guys, bye.